Ah, the 8 puzzle, my old nemesis. I hated this as a kid. If you haven't played it before, the basic idea is you can slide tiles into the empty space, and your goal is to get it so the tiles read 1, 2, 3, 4, 5, 6, 7, 8, and then have an empty blank in the corner. Now the vexing thing, of course, is I want to get the 3 up there, but it seems like, wait, I'm going to have to move the 2 out of the way? Did not like that as a kid, just seemed, I don't want to undo what I've done, my beautiful solution. So in this problem, what you guys are going to do is write a program that can actually solve the 8 puzzle programmatically. And not just solve it, because if you randomly move them around, eventually you'll get lucky, but also to find the minimum length solution from a given starting state. So if it looks like this, I could tell you exactly the moves you need so you can impress your friends by cheating. As an example of what you'll be doing specifically, you're going to be given an initial board state, in this case, blank tile, 1, 3, etc. And you're going to find the minimum sequence of moves, in this case 4 moves, that get us to the goal state. Now we're going to do that using an algorithm called A star, which is a general purpose algorithm for doing searches, not just a toy problem like this, that's going to take into account which moves are better than others. So for example, this 1, it makes more sense to move the 1 over here than to bring the 4 up here, because this is closer to the goal state. And we'll talk more about that in a moment. By repeatedly using that kind of heuristic, we'll eventually arrive at the best solution. Now one thing is that if we want to have a fast algorithm, A star is only going to be efficient if we use our brand new data structure, the heap-based priority queue. Before we dig into the details of the A star algorithm, let's discuss the humble board class. So the board class, it's going to have a constructor that's going to take a 2-dimensional array of integers that's going to tell it what the board state is, and it'll be up to you to decide how you'd like to represent that. You can represent it with a 1D array, a 2D array, maybe something more exotic, and it also has a number of functions that tell us about different aspects of the board. For example, its size, or, very important to our discussion now, the Hamming and Manhattan distance. So to explain those ideas, I have here a particular board state, and we're using 0 now to represent the empty square. So if you'd like, you can imagine it's blank, but I will not, consistent with what maybe you will do with your representation. So here is the board state, and here is the goal board. So the Hamming distance is going to be the number of tiles that are not in the correct location. So for example, 7 is in the wrong position. We also observe that 4, 5, and 8 are in the wrong position. And our convention with our assignment is that we don't count the 0. So in this case, there are 4 tiles exactly that are out of position. So the Hamming distance is just 4. The Manhattan distance measure is an alternate method that's going to tell us not just how many tiles are out of place, but also how far they would need to move. So for example, the 7 would need to move 2 times to get into position. So we'll make a note that's 2 for the 7. The 4 would need to move 1 position. If we look at the goal board, the 5 would have to move 1 position, and the 8 would need to move 1 position. So the total Manhattan distance would be 2 plus 1 plus 1 plus 1, which is just 5. The last method we need to understand before we can move on to A star is neighbors. So for every board, that board may have as many as 4 neighbors, which will return as an iterable. Now it's not always 4. For example, this puzzle has only 3 neighbors, corresponding to sliding this 1 down, the 3 over, or the 6 up. So if we go back to our example with Hamming distances, we can start to tie this together. Here's a board where we have 3 neighbors, because here's the empty tile, just like we just saw, and each of these 3 neighbors has its own Hamming distance. And we can imagine repeating this process over and over until we get lucky enough to find the goal board, and then we just need to follow the sequence of arrows back up to the original board, and that will give us a solution. Now we can't always take the optimal move. You might not necessarily go to the one with the smallest Hamming distance, because as we saw earlier on, that was exactly what vexed me as a kid. Sometimes you have to undo your work in order to get to a better solution ultimately. That's where A star is going to come in. Before we talk about the A star algorithm, let's do a small example by hand. Suppose we have a board in this state, and we want to find the minimum number of moves. We observe that this one right here has Hamming distance 4. And so what we can do is, well, to find the goal, we're going to have to obviously make some set of moves. So let's consider each of the 3 boards that come out of this board. So we'll put a little blue X here to indicate to ourselves that we've already thought about this. And now we find that we have 2 neighbor boards with Hamming distance 4 and 1 with Hamming distance 3. So what we could do is then list both of the neighbors of this board, all 4 of these, and both of this board's neighbors, and just keep repeating that process, building out this exponentially growing tree of boards, and then as soon as we see the goal, boom, we know that's the minimum number. Now that algorithm would be easy to code up, and it would work definitely to find the minimum number of moves, but it would also take an exponential amount of memory and an exponential amount of time. So you imagine that, for example, the number of moves that must be made is m, then you might end up making as many as 4 to the m boards. And considering some of these boards can take 40 or 50 moves, as you'll see from the given data set, 4 to the 50 is a pretty gigantic number. So we're going to have to do something a little more smart. What we can do is think about these 3 boards and say, well, this one seems a little better, right? This board in particular has a handing distance of 3. So I keep thinking about how I said a little more smart instead of smarter, by the way, so please forgive me. Anyway, so this board right here has a handing distance of 3, which seems a little better than these because, hey, we've made a little progress, whereas these, maybe I'm just treading water. So I might consider just the 2 neighbors of this board next. So I exit out, make a note to myself, and I look at these boards. Well, I look and I see that no matter what I do, I'm undoing a little work. Curse the gods. Well, what do? We have to make a decision now. We could enumerate the next states of this board, this board, this board, or this board. So which one's best? Well, you might observe that this board right here and this board, they're the same board. So maybe this one wouldn't be such a good choice. But maybe we can come up with something a little more general than that. And also we have to resolve among these 3 which one's best. Well, I'm going to argue that these 2 boards are better than this one. Because to get to this board, I already have to have made 2 moves. So we can think of these boards, actually we can annotate each board with the number of moves we had to take to get there. And this gives us a very important piece of information. I can think of the sum of these 2 numbers as a measure of how good that board is. Or more concretely, let me fill in the number in each state. I can say that this number right here is the lower bound on the number of total moves needed to solve the puzzle. So of course, if I'm in this state and the distance is 4, then I know I'm going to have to move this little black square around at least 4 times because we can only fix one problem each time. And we know we've already made 2 moves. So in the very, very best case, I know that this thing is going to take a total of 6 moves. There's no way it could be less. By contrast, these 2 boards could take maybe only 5, right? I mean, it'll probably take more, but that at least gives us a lower bound. So what that number tells us then, that lower bound gives us a measure of the quality of a board. One thing we could think about, we could also maybe call this, I don't know, priority. And what we could do is, in order to decide what move to make next, we could just throw all of these things into some kind of magic priority tracking data structure we might have learned about recently. And then we can just keep pulling out the lowest priority item. So each one of these positions of the board will have its own priority, and we'll keep making the best move instead of making all moves, which, as we mentioned, will be exponential. So the next thing that happens maybe is, let's say this guy gets deleted off the priority queue. It has 2 children. I'm showing one of them. And then there's some other neighbor I'm not going to show because I'll run out of room on the slide. Next up comes one of these 2 nodes if we're deleting it from the priority queue. And I'm going to say it's this one. It could be either, though, because, ties could be broken in any way. But let's say this guy gets deleted. Now, he has 3 neighbors. And again, I'm only illustrating one of those neighbors. So these arrows, there'd actually be 2 little boards there, but again, space constraints. And what we'll observe is each time we make one of these moves, it happens that the handing distance is decreasing. These are pretty good moves, hence the reason I'm showing them. And so the priority for all of these is still 5. And so even though these boards have been sitting in the hopper for a while, waiting to come out, these guys keep cutting them off. So next one comes up, maybe this guy gets deleted, and he actually has 4 neighbors because it's the 0 in the middle, so 3 of them are not shown, and we end up with this board. And then finally, we delete him, and we see, the goal board. And now we know that this is a solution to the 8 puzzle. So what's this fancy A-star algorithm we're supposed to be implementing? Well, it turns out that what we just did is A-star. So A-star is just a general algorithm for traversing some kind of space where we have a starting position and a target position, and we always take the expected lowest cost move. That's A-star. So in order to know what the expected lowest cost move is, we need a measure of how far we've come so far, walking through the space, plus an estimate of how far away the goal board is. So what we did matches that. We saw before that when we found the goal board, obviously that is a path. Now, one thing I didn't say before is that this right here, our future cost estimate, as long as it is never an overestimate, A-star guarantees that you always find the minimum length path. So it's something you can try and prove to yourself if you'd like. And if you're curious, you can go check out the Wikipedia page linked from the assignment page about A-star and see how it can be applied to other types of problems, like, say, maze traversal. Let's talk just a little bit about the implementation details for A-star. So that solver, the A-star solver, is going to live inside this solver class. It's not going to be inside board. And you might ask, okay, well, what am I actually going to be making a priority queue of? I mean, am I making a priority queue of boards? How do I know the priority? The answer is no. Actually, of course, you cannot use a priority queue of just boards because a board doesn't know how many moves it took to reach that board. That's higher level information than what board cares about. So what we recommend in the spec is that you should build a private class called search node that needs to track various pieces of information. Of course, it needs to have a board in mind, and it also needs to know how many moves did it take to get to that board. So if we've just started solving an 8 puzzle, the initial board state is going to have 0 moves. We'll also have a priority for each node, which is exactly as I've just described, and then we'll have a previous pointer that we can use to actually work our way back to the starting goal so we can return the sequence of boards that you had to take to get to the solution. So each of these, remember we had an arrow. We need to keep that arrow around for our search nodes, okay? So it's up to you to figure out exactly how the search node class should look, but that's roughly how it looks. So given a search node, after we delete this thing from the priority queue, we're going to generate its 3 neighbor search nodes. So I'm going to give away one of them for you real quick. So here is a search node. It's one of the neighbors. And of course, if you implemented your board class correctly, it'll be able to tell you the Hamming distance because that's part of board. And then we also need to set moves, priority, and previous as appropriate before we put it in the priority queue. So naturally, the number of moves to get here is 1. So that means the total priority should be 4, and the previous pointer is always going to go to whoever the Papa node was. All right? Now, there's 2 more nodes, and what I recommend you do right now is pause the video, and I'll just stare solidly at you while you do that, and try and figure out these next 2 nodes. So go ahead. All right, hopefully you got that. These 2 search nodes have priorities 5 and 6 respectively. And so all 3 of these search nodes are going to be put on your priority queue. Now, how does it know which one of these numbers to use as the priority? I guess that probably means you're going to have to either make search nodes comparable or you're going to have to make some kind of comparator so that MinPQ knows what to do. This seems as good a time as any to address a common complaint we get from a small number of 226 students each semester, which is that on the assignments, we give away maybe a little too much in their opinion. So for example, now, I've been so gauche as to suggest you should use a search node. It should contain this information. It should go in a priority queue, and so forth. So for those of you who intend to go further with computer science, rest assured, in future classes, you'll have plenty of room for open-ended design problems. Furthermore, on this assignment, there's a number of extra credit opportunities and optimizations that you can implement if you want to go beyond just the core of the spec. There's one last big idea in this assignment that we need to know about, and we're going to get there in the context of history. So this right here is a 4x4 version of the 8 puzzle. And in this case, this particular state of the board is the same thing as the goal, but where the 14 and the 15 are reversed. Well, it turns out that in the late 1800s, there was a prize by Sam Lloyd that anybody who could take this puzzle and switch these 2 things so we get it into the goal using some sequence of moves, he would pay them $1,000, which in the 1870s was quite a lot of money. Now, as it happened, at the time this puzzle was, or this challenge was offered, it had already been proven impossible to do a decade earlier. But at that time, he couldn't just go Google and find, okay, it was impossible. Now, and we'll talk a little bit more about this in a minute, because what you're going to have to do is, given a particular board, say whether it's solvable or not. But I'd like to just, if you'll forgive me, a detour into the strange world of Sam Lloyd. So Sam Lloyd, in addition to having this bogus prize, the last 20 years of his life, he suddenly decided that he was going to take credit for the creation of the 15 puzzle. And I mean, 15 puzzles are big. I mean, here's a political cartoon where everybody, it was pretty fresh at the time. But there was a point in time where there was a craze about this thing. It was like Doges, or all your base or belong to us, or tulips, or one of those things. And Sam Lloyd, long after the craze had passed, was like, okay, well, hey, I'm the 15 puzzle guy. And if you look at his Wikipedia article, this is even more surprising because he was like a real guy who did a lot of puzzles, and he's well known for his interesting chess puzzles, but somehow he decided like he just wanted to take credit for this, but it is amply documented that he was just making it up. Now, it turns out that his PR campaign over a century ago was pretty successful. If you look at our old version of the assignment spec from spring 2007, you'll see it says that the 8puzzle is a game invented by Sam Lloyd. Only later do we catch on and realize that, in fact, it was invented by No-Yes Palmer Chapman, as I've decided it's pronounced, who, by the way, has no Wikipedia page. It turns out that we can tell a board is solvable with a parity-based argument. So it's something like a chessboard, where we can divide all boards into two equivalence classes, kind of like a bishop on a chessboard can either be a black square bishop or a white square bishop. And you can never move between those two sets, but within one set you can reach every state within that set. So the argument, we'll do it in two parts. The first will be based on an odd board size. And what we're going to do is think about the number of inversions in this array. So our board, we can unroll it. It's, in this case, 3 by 3. But we can unroll this into an array of length 8, right? So 1, 2, 3, 4, 5, 6, 8, 7. So 1, 2, 3, 4, 5, 6, 8, 7. In this particular case, we have one inversion. And by inversion, I just mean exactly what we had from the sorting lecture. So if we move the empty square either to the left or to the right, of course, that's not going to change this array in any way, right? Because if you think about what happens as we unroll this array versus this array, they're going to result in the same one-dimensional representation. So the number of inversions does not change with a horizontal move. Now with a vertical move, when we move 5 from here to here, we are always going to be effectively moving the 5 2 positions in the array, right? So we move it here, and whereas before it used to be before 6 and 8, now it is after 6 and 8. So if that happens, if you move an element in an array by 2 positions, you're either going to change the number of inversions by 0, or you're going to change it by 2. And if you're not convinced of that fact, I mean, that's something you have to think about, but convince yourself that a vertical move could only change the number of inversions by 0 or 2. So what that means is, let's suppose we start with a board state, which has one inversion. Then we can either change it by 0 by using a horizontal move, or maybe if we do the right kind of vertical move, we can change it by 2. But there's no way to get this inversion count down to 0, so there's no way to reach the goal state. More concisely, we can say that the goal board has 0 inversions, so if we can only change the number of inversions by 2 at a time, if we start at some odd number, let's say 3, there's just no way we can subtract off 2's and get down to 0. The argument for the even board size is a little more sophisticated. So in this case, what we're going to do is track the number of inversions and the row number in which the blank element resides. So, oh, and by the way, the even-sized board means something like a 4x4 or a 6x6 or something like that. So anything like that, we have to do the smarter argument. So what we'll do is, just like before, we're going to track the number of inversions. So in this case, there are 6, and that's not an obvious fact. I mean, that's something you'd have to actually sit down with this array and derive. And we're also going to compute the row. We're going to keep track of the row in which the empty space resides. So in this case, 0, 1, 2, 3. And then we're going to do a weird thing. We're going to add those and compute a sum. Now it seems like some kind of unit mismatch. Like it's like we're adding like pounds and like feet or something. Like, what would that even mean? Well, just trust me. So if we move this blank space to the left or right, what happens to the inversions? Well, of course it doesn't change. And of course the row number of the empty element won't change because it's a horizontal move. Now if we do a vertical move, like so, in this case, the row number is going to change by 1 or minus 1, and the inversion number is going to change by minus 3, minus 1, 1, or 3. That's a non-obvious fact that you would have to actually sit down and convince yourself of. But what that means is that ultimately we have 2 odd-numbered changes here, which means that the total sum of this weird quantity that we're summing up is going to change by an even amount, okay? So this magic quantity always changes by an even number no matter what you do. Now, as it happens, the goal board has the property that has 0 inversions, and the blank element is in the 3rd row. So what that means is, if you're in any board where this magic quantity we've just made up, that's the sum of these two things, is even, and we can only change it by an even number, of course we can never reach 3. So what you're going to have to do is keep track of the blank row and the number of inversions, and that will tell you whether or not a board is solvable. Whew, it has been a long video. I hope you're enjoying it. Just a little more to go. So I want to talk about a couple of practical details that you might have missed in the spec. First of all, of course, make sure you look at the performance requirements. That's very, very important. And you have to use the min-pq data type for A star. It's not that we think min-pqs are better than max-pqs or some alternate version of maybe a built-in priority queue. It's that for our autograder, we have to do some sneaky stuff that assumes that you use a min-pq. And while I'm at it, I'll mention that if you really enjoy programming, we're always happy to get help with autograder development in the future. So when you get done with 226, talk to me or Kevin. It could be pretty cool stuff. Make sure to note that we give you guys a solver test client and a number of test files. And they are conveniently numbered by the number of moves needed to complete the puzzle. So puzzle 20 should take 20 moves to solve. Now that doesn't necessarily mean that they get increasingly difficult. Certainly I don't remember exactly which ones, but there are some that will take a really long time. Feel free to post on Piazza about which ones seem to be taking you a long time, but there's no official documentation about which ones should be completable and which ones should not. Two last things. One is, for the method where you have to compute the neighbors of a board, right? So I'm given a board and I have to find the 2, 3, or 4 neighbors of that board. You return it as an iterable. So what's an iterable? Well, that could be a stack or a queue or anything that implements iterable. Now, one very, very important thing is that in another class, let's say solver or any other test code you write, you should never, ever cast an iterable as its base type or whatever underlying type it is. So for example, suppose you use a stack in board whenever you return this iterable. And you might say, okay, well, x.neighbors gives me an iterable. I know, I'll just cast it to a stack, and then, hey, I now have a stack that I can push and pop from instead of having to use that annoying for notation. Don't do that. Because of the fact that maybe us, maybe someone else will replace your board implementation with something that uses a queue or something else. If something's iterable, it is very unsafe to cast. Just in general, you should avoid client casts if at all possible. And the very last thing is the equals method. So when you talk about whether or not 2 boards are equal, make sure you follow the rules laid out in the lecture, as also in the book, explaining how to write an equals method. So there's a lot of little details mentioned here, or there's a list of rules here, and the compiler might not check all of these things. I mean, the autograder will, but watch those equals tests carefully. It's very easy to get them wrong. So all of that said, I hope you have a good time with this assignment. It's pretty cool to finally defeat the 8 puzzle without even having to think. Thanks. Bye.